For the autonomous mission in the University Rover Challenge, the rover needs to be able to navigate by itself, and in order to do this, it needs to be able to detect obstacles, to map out its surroundings, and to know where it is itself. And so these two cameras should be able to help with that.
Yeah, so last year they got the Intel RealSense depth camera, that's this camera here, and it can get distances away from it and creates an array of, or a two-dimensional map of depth points. And then they were able to get it running, but not able to utilize it to the best ability. So we decided that this year we could benefit from incorporating that depth information with rotation. And that's what this tracker does. It's from Intel as well. And it gives rotation as well as translation. And so with that set of information that could represent an object or something, we can create a map of points that can be updated as the rover moves in position. And our video, as you will see in a second, will demonstrate that updating of information as it moves throughout the hallway of the building.
Hi, my name is David Crummett, and I am the Manipulation and Ops Lead for the Mars Rover team. Today, I'll be demonstrating a proof of concept for a new arm mount assembly. I unfortunately do not have a hard prototype as my 3D print failed halfway through, and it takes 22 hours to print a new one. So today, I'll be using SolidWorks. What we're looking at right now is actually a picture of what's currently on the rover. The arm will come down and attaches to this black block right here. And what's hard about this is the hardware you have to be able to reach in order to screw anything in. Is you have to do all your work in this little spot right here, and that can take way more time than we have. So we need to come up with an alternate solution. One of the solutions that we do have is, instead of like you mounting down like that, you mount on the sides. To demonstrate, is this block would actually be more or less permanently attached to the arm, whereas this block would be permanently attached to the top of the rover itself. And you can just easily screw in this way. And the reason why we do that is so we can easily just set it down on the mount and put four screws in. There'll be 4 holes, 2 on each side, like right here. You can see the 2 right here. And I'm only demonstrating with 1 screw for simplicity, but the screw would go through this hole. And to make it even quicker, easier, we could have either a captured nut on the end, or since we're considering making this out of aluminum, we could thread it and put a thread insert in. That way, all you have to do is get in there, tighten it. You don't have to worry about holding a nut on the other side. This new design could speed up assembly exponentially.
This proof of concept video showcases 3 changes in the power and drive systems. The first is a decrease in battery voltage from 15 volts to 12 volts. This is to decrease the current draw from the motors, resulting in lower power consumption rate. From this and other testing, we've determined that the drop in performance is acceptable. The second change shown in this video is using smaller motors and an increased gear ratio to deliver the required power while balancing torque and top speed. We feel confident that this combination will meet our needs for competition and are excited to test these systems on last year's rover.
Hi, my name is Michael Kirk. I'm the science lead for the USU Mars rover team. For the competition, we have to collect a dirt sample and analyze it for life. And today I will be demonstrating a proof of concept for a Venturi vacuum system. So right here, I have a pretty simple Venturi device. It has a tube that is formed a little bit of a nozzle on this end, a port where I can hook up compressed air, and then just a bag to collect things in. So if I come here and attach the compressed air, it'll blow air through it that way and create a vacuum on this end.
I'm going over the autonomous guidance and obstacle avoidance aspects of the rover. We're planning to implement a weighted vector field pathfinding algorithm. To start, I just wanted to show how the approach could run into some trouble, then I'll show a few ways it can be changed and refined to not only ensure mission success, but help optimize the path taken. Basically, the rover, our little blue arrow here, is guided to the goal using vector fields shown by the green lines. You see the goal up here in the right-hand corner. Now we can see the rover's gotten stuck here trying to navigate through the obstacles. This is due to the relative strengths of the attraction and repulsion vector fields guiding the rover. In this case, the attraction field guiding it toward the goal isn't strong enough to overcome the repulsive fields, keeping it from colliding with the obstacles. Now I'll reduce the values governing obstacle avoidance to allow the rover a closer approach to the obstacles. Doing this means the rover gets fairly close to the obstacle before changing course, but it should give it enough leeway to get through the gap between those two. We'll see it here. As we can see, it does approach closer, but then we get this oscillating motion as it tries to navigate around it, and it does get nearly trapped toward the corner there. I could tweak these settings further to refine the path, but there's another approach that will simplify things quite a bit. What we'll go ahead and do is implement an orbit avoidance method. Once the rover detects an obstacle, it changes course fairly immediately to orbit around the obstacle at a prescribed distance. Now we'll see here, it's going to approach the first obstacle and then change path once it gets within a certain distance, whatever that prescribed distance is. It changes path immediately and then orbits around the obstacle at pretty much that distance. And we can see it was a little bit smoother path, and it did make it through the obstacles a little bit more quickly there and goes on to the goal unimpeded. Now, we can see that this has advantages and over the previous method. We can also go ahead and change the goal location to just kind of show how this method will also deal with a little bit more challenging obstacle avoidance path here. Let me show you. We can see we've placed the goal just on the other side of that triangular obstacle, and it does take a bit more time and cuts very closely around the corner, but we can see that it is able to still get around that obstacle with this orbit method. The advantages here with the orbiting method are clearly enough that makes it worth it trying to use this. So this is the method we have chosen to use obstacle avoidance, and vector field pathfinding.